Hi everyone, welcome to my YouTube channel. In this video, I am going to explain you about very important topic from quantum mechanics, that is particle in one dimension potential well. Okay, so this is very important topic, and many of the questions have been asked on this. Every time the questions will come on this. Okay, before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. Let us start here. So the particle in one dimensional potential well. This is one of the application of Schrodinger wave equation, as we have particle moving freely in space and particle in one dimensional potential well and three dimensional potential well. So first we try to understand here particle in one dimensional potential well. So as it is here, one dimension means along x-axis or any of the coordinate you have to take. So consider a particle of mass m moving inside a box along the x-axis between x equal to 0 and x equal to L. So let the potential V of particle inside the box be 0 but rises to infinity outside the box. Okay. We have the limit here x equal to 0 and x equal to L. In between this value V is equal to potential is going to be 0 as V reaches to the boundary or outside the potential well. This is infinite potential well of height infinity. But it rises outside the potential well or between the boundaries. So within this range V is equal to 0. So thus we have two conditions here. V equal to 0 for x, the particle lying between 0 and L are the walls of potential well, and V is equal to infinity when it is greater than 0 or outside the wall. X is greater than L. X is less than 0 or x is greater than L. So we have these two conditions. V equal to 0, V equal to infinity. So the Schrodinger wave equation for the particle within the box is given by, so we have to consider here potential between x equal to 0 and x equal to L. So for this the Schrodinger equation is written like this: dou square psi dou x square plus 8 pi square m into E divided by h cross square divided by into psi is equal to 0. Take this as equation 1. So let us consider here this second term as k square, constant k square. Okay. So if we put k square in the equation 1, we will have this second order derivative along one dimension. Dou square psi by dou x square is equal to minus k square psi. So the general solution for this differential equation is given by the wave function as a function of x, a sin kx and b cos kx. So this is the general solution of the second order derivative equation 3. Then a and b are what? Constants here. Since the particle cannot have the infinite energy, it cannot exist outside the box. The condition we can see here, particle will exist within the box potential well, but if it is outside, then we can say that cannot have the infinite energy. So hence the wave function psi must be 0 at x equal to 0 and x equal to L. These are the boundary conditions. Okay, x equal to 0, x equal to L, psi is going to be 0 because cannot have infinite energy. That particle exists outside the box. So then wave function is going to be 0. From the boundary conditions, we can write psi, the equation for psi of x equal to 0 at x equal to 0. First condition, if we take, if we put x equal to 0 in equation 4, psi is equal to 0, a sine of 0, b cos of 0. So sine 0 is 0, b is equal to cos 0 is 1. So b is equal to what? 0. Then we have another condition, x equal to L. So if we put x equal to L in equation 4, if we get a sin KL plus b cos KL equal to 0. Okay. Then it is possible only when this is equal to the sum of these two is equal to 0. This is possible when KL is equal to n pi. Okay. Here KL, if we put KL is equal to n pi, sin pi is equal to what? That is going to be 0, cos pi 1 minus 1. So k is equal to, we will have, here we can take n pi by L. Then n, what is the value of n here? N may have the integer values n equal to 1, 2, 3, which are called quantum numbers, principal quantum number. Substituting the value of k in equation 2, we get equation 2 is which one here? This k square is equal to 8 pi square m e by h square. If we substitute in equation 2, we will have the equation for energy. Okay, energy for nth term En. So energy eigenvalue, that is given by n square h square divided by 8 pi 8 m L square. So this is the equation 5. This is very important. From this, many questions are going to be asked on energy eigenvalues of potential well. From this equation, it is clear that particle in a potential box cannot have an arbitrary energy, but it can have discrete energy, En, as we know. So n can have the values of 1, 2, 3 and so on. That's why energy here is not continuous, it is discrete in nature. So from figure 3, if we take boundary conditions x equal to 0, x equal to L, and we can take values of n equal to 1, n equal to 2, n equal to 3. So energy eigenvalues E1, E2, E3 we will get. So E1 is equal to what, n equal to 1, h square divided by 8m L square. So like that E2 4h square 8m L square. So like that E3. So these are called eigenvalues of particle in a box. The bound particle has quantized energy. So according to Planck's theory, energy is discrete in nature. So whereas for a free particle, L is equal to infinity. Now the spacing of energy levels become infinitesimal and hence they appear to be almost continuous spectrum. For free particle, the value of L, the boundary condition is going to be infinite. So energy is not discrete, energy is going to be continuous for free particle. If energy is in a potential, one dimensional potential well, energy is going to be discrete in nature. For a free particle, energy is going to be continuous. So then E is equal to, for free particle, h square k square divided by 8m pi square for free particle. Okay. So from equation 5, we can have these conditions here. First one, the lowest energy of the particle is obtained when n equal to 1. Now the energy becomes E1, h square divided by 8 ml square, and nth energy we can write En is equal to n square times E1. In general we can write here. So it is known as 0 point energy. When energy is going to OB, we call that as 0 point energy when the lowest energy n equal to 1. Okay. Second condition, the possible value of energy in the potential box are discrete corresponding to n equal to 1, 2, 3. So as we know, energy is going to be discrete in nature. The third one, the spacing between the nth energy level and the next higher level increases as if we take the difference between ground state and excited states, or spacing between nth energy level and the next and higher level, we can write the equation like this: spacing between energy levels n plus 1 square E1 minus n square E is equal to 2n plus E1. So these are the few conditions related to one dimension particle confined to one dimensional potential well. So this is all about energy eigenvalue and the boundary conditions for particle in one dimensional potential well. And many of the questions, compulsory question will be on energy eigenvalue, En, nth energy. They are going to ask in exam. So I hope this video is helpful. If it is helpful, please like, share and subscribe my channel. Thank you for watching.